Do you feel a tiny surge of eco-friendly satisfaction whenever you use one of these compostable bioplastic straws? It feels like we're saving the planet, right? You might even think that if you accidentally drop it in the soil, it'll just melt away in a few days. Well, I'm sorry to burst your bubble, but that is a massive misconception. Today, from a material perspective, let's unpack why these green polymers might actually be creating a whole new environmental headache, and how the future of plastics might literally be grown from nature. Traditional petroleum-based plastics contribute heavily to global carbon emissions. To solve this, materials scientists developed biopolymers. The most common one on the market right now is PLA, or polylactic acid. PLA is derived from renewable resources like cornstarch, which is fermented into lactic acid, and then polymerized into long PLA chains. Structurally, PLA is linked together by ester bonds. In theory, when ester bonds meet water, hydrolysis occurs, breaking the polymer back down into harmless lactic acid. That's the scientific secret behind its compostability. However, if the chemical structure allows it to undergo hydrolysis, why does a PLA straw buried in a normal backyard look exactly the same after 3 months? The answer lies in polymer kinetics and thermodynamics. For PLA to hydrolyze efficiently, it requires very strict environmental conditions, namely high temperature and high humidity. The glass transition temperature of PLA sits around 55 to 60 degrees Celsius. At normal room temperature or standard ambient soil conditions, the polymer chains are completely locked in their crystalline domains. Water molecules simply cannot penetrate the structure. Therefore, without industrial composting facilities that maintain these high temperatures, PLA remains intact for years, making it an imperfect solution for open environment littering or marine pollution. This limitation is precisely why the next generation of biopolymers looks toward the ocean. What if we could extract polymers directly from marine life, like seaweed? Enter sodium alginate, a natural polysaccharide extracted from brown algae. By utilizing simple ionic cross-linking with divalent cations like calcium ions, we can create instantly biodegradable, flexible packaging. Because it is a natural carbohydrate structure, it dissolves and breaks down completely in water, without leaving a single trace of toxic microplastics. But what if we need something tougher? What if we need a material that behaves exactly like synthetic durable plastic, but still degrades naturally anywhere it lands? That's where PHA, or polyhydroxyalkanoates, comes into play. Unlike PLA, PHA is naturally synthesized by specific bacteria as an internal energy reserve, much like how humans store fat. Because it is produced biologically, nature already contains the widespread microbial enzymes required to break it down. PHA doesn't need an industrial composting facility. Whether it ends up in the open ocean or in your backyard soil, microorganisms can fully metabolize it into carbon dioxide and water within a matter of months. From petroleum-based plastics to PLA, and now to the future of seaweed-derived alginates and bacterial PHAs, the evolution of polymers shows how chemical engineering actively addresses modern ESG goals. Turning natural resources into sustainable materials offers an incredible path forward. But the ultimate solution still relies on reducing single-use waste. Technology can provide better alternatives, but our daily habits are what truly change the world.